Hello everyone, my name is Kiran and I would like to present about our project on text restoration using image super resolution. First, let us start with the motivation behind the project. Text recognition is an increasingly popular application of computer vision, especially with the advent of deep learning techniques. This in turn sees various applications in domains such as document retrieval, scene understanding, the restoration of historical manuscripts such as old newspapers and historical documents, autonomous navigation, etc. However, most text recognition models work well for constrained settings such as scanned documents. Tends to fail for low resolution images and images that contain text in natural scene data. To combat this, super resolution has been proposed as a pre-processing step so that the low-resolution text images can be converted to high-resolution text images. However, this is difficult because most super-resolution models are developed for natural scene data and not for text data. Challenges can arise due to the complicated nature of text, including structural information like fonts, languages, orientations, etc., as well as background conditions such as lighting, contrast, texture of background, etc. In our study, we have done a comprehensive review of related literature. We discussed the history of image super resolution, the advent of generative adversarial networks, and its applications in the super resolution task. The text zoom dataset was introduced for the task of scene text image super resolution. Although this dataset was a breakthrough in the domain itself, it has severe limitations. The high resolution images provided in the dataset often contain degradations, and the images are of low quality. The limitations of this dataset makes the TextZoom dataset unsuitable for practical training purposes, and hence motivates us to build a high-quality text-image dataset that can be used for scene text-image super-resolution tasks. For this, we create two datasets. One is a synthetic dataset of English words generated randomly. These are arranged in different orientations, font sizes, and fonts. The other dataset consists of scene text images, which is scraped from the web using keywords such as billboards, street signs, etc., and is cropped to the text bounds using the text detection models. Here is an example of a street signboard, and the text images that we obtain below after detecting and cropping the text. And now that we've collected the high resolution images, we move on to construct the low resolution images. For the low resolution images, we use several degradation processes. This includes the blur degradation, where the details become less defined and softer, which can occur due to camera shakes, out of focus lens, and atmospheric effects. We can also have noises in the form of Gaussian noises, which is additive, and Poisson noises, which is multiplicative, which is often caused due to limitations in sensor quality. There can be downsampling due to a reduction in pixels in different methods. Finally, there can be a JPEG compression loss, which is a lossy compression technique. However, we find that these degradations are too simple, and hence, we use a higher order degradation process. It consists of multiple degradation steps of the different degradation processes described earlier in different combinations. For our research, we use a second order degradation, and we can obtain an image as seen in the example over here. The low resolution images are generated by the network on the fly during training. The model is useful for practical purposes. The training network follows the real ESR GAN architecture. The generator network can be shown over here, which makes use of the residual dense blocks combined with skip connections. To train the model, we have three loss functions: the L1 loss, based on mean absolute error, the perceptual loss, which can be used to capture high-level image characteristics such as edges, etc., and a GAN loss, which is adversarial loss for training the generator and the discriminator. Finally, we move on to the results we have obtained. First, we compare the outputs of a model trained only on the synthetic data and the model trained on a combined real-world and synthetic data as against the pre-trained model. We first see the outputs on the performance of the synthetic data. As you can see, the model trained on the pure synthetic data and the combined data can capture the structural information of the text more accurately as compared to the pre-trained model. On the real world, however, we observe that the data trained on the synthetic model trained on the synthetic data fails to capture information specific to color and structure in scene images. As such, the combined model can capture the text better in scene images as compared to the pre-trained model as well as the synthetic model. From the observations on the different images, we can observe and validate the need to collect high-quality text images with both real-world and synthetic data for effective super resolution. The quantitative results affirm the same. We compare the PSNR and the SSIM values across the different models that we have. And we see that these metrics are the best for the model that's trained on the combined data set on the real ESRGAN architecture. The scene text resolution, scene text image super resolution is a very challenging task, and our study was an attempt to improve the performance by improving the quality of data. However, this model is far from perfect, and we can see a further improvement by further refining the training data, include more cases of synthetic and scene images to cover more scenarios. Further, the network can explore the use of text-based loss functions, such as the CTC loss, to boost the performance of the model. With this, I've come to the end of the presentation. Thank you.